Okay, I hope the screen is visible. Yeah. So the question last week was regarding about the energy balance, right? So in energy balance, we have enthalpy as the main factor that we are considering. So in that case, uh, you must be aware of the notations that H is the enthalpy, and we generally use the small h in the place of enthalpy per kilogram or per mole, which is specific enthalpy, whereas the capital notation, capital H that we use is generally for the total energy. Okay, so the general energy balance equation is your mass that is getting into the reactor into the specific enthalpy. Like let's say some 20 kg is going inside. You know the enthalpy per kg, then obviously you will multiply. So that's this very basic concept. Like here, if you can see the mass that is going inside, but in continuous reactors, the fact is that m will be given in terms of kilogram per minute, like per minute or per hour, whatever notation that is, for a given time how much mass of the feed is entering the reactor. So in that case you should use that as it is. So the mass into the enthalpy, specific enthalpy of the substrate that is getting in, that will be there, and you are also at the same time removing something out of the system. So the mass that is being removed out of the system and the specific enthalpy of the product that is removed, so that is subtracted, and then another heat that is getting out of the system. So the mass in into Hn is the energy that is getting into the system. The mass out and the H out is again coming out of the system, and Q is the heat removed from the system, and Ws is the amount of work that you, like the power that you give for the shaft to rotate. Because you give some power and the shaft is rotating, there is some heat liberated. Okay, but you are giving an energy input, so the shaft work supplied to the reactor is Ws. So if you have the amount of, in what all ways energies can go into the reactor and come out of the reactor, so that is your energy accumulated inside the reactor. Okay, that is del E term. So this is the first equation. So you have to use this equation when your question is having your feed and outlet stream, like how much kilogram per minute or how much moles per minute is entering the reactor and what is the specific enthalpy. All this you can, when you have this data, you can use this. And we also know that at steady state energy does not accumulate. So del E is equal to 0. At steady state, del E is equal to 0. And like we also have one more equation where we have the same equation as above, but there are just two terms different here. We don't have the mass in Mn Hn minus M out H out is the minus del H reaction here. So what is the net total enthalpy of the reaction itself? That we directly have. And one more thing in biological reactor is evaporation. So how much of, because your heat is getting generated, heat as energy can leave the system, or how it leaves is like in the form of water. So the heat travels along with the water, it takes water along with it in the form of vapor and leaves. So for that you use the term mv del hv, so which is the latent heat of vaporization term. So this is for a simplified biological reactor version of the energy balance. So the first one that we saw was a standard version. The second one that is the just for a biological reactor. So you have to use this equation when the problem already has the del heat of reaction instead of the inlet and outlet enthalpies. You will not be given this specific enthalpy. The small h values are not given directly. Your del H reaction value, if it is given, then you can use this. And for exothermic reaction, del H reaction is less than 0. So that's why the negative sign we are having here, and the negative sign means that the reaction is going to release heat. So to put it together, you can calculate del H reaction in multiple ways. The first thing is, see, del H reaction is your mass of your substrate into the specific enthalpy of the substrate. So you have product term and reactant term. In product uh, term, you will have your biomass as well as the other products that are formed, and in your reactor term you will have your substrate and your nitrogen source, which is your carbon source and your nitrogen source. Ideally your substrate, which is the carbon and the nitrogen source, is going to enter the system, whereas the biomass or products are going to leave the system. So you have whatever is the energy that is entering the system minus whatever the energy that is leaving the system. So here the del H value or the specific enthalpy or the heat of combustion is given. Apart from this, there is one more way to calculate the heat of reaction. So that is when the process is aerobic. Instead of, see, for individual product, you should know the del H value. If that is not known, you can also calculate the del H reaction value based on how much of oxygen is being consumed in the uh, reaction. Okay, so here what you do is you have this formula for del Hc naught, which is minus Q gamma Xc. So here your molar heat of reaction is based on the oxygen consumption itself, right? So for that only you are using, and how is your oxygen consumption you can calculate? It is based on the degree of reduction of the compound. So you use how much of heat, specific heat is there, how much of what is the degree of reduction and what is the number of carbon atoms. Based on this only you can find the molar heat of reaction for oxygen consumption. So for a given compound, this much amount of oxygen heat of combustion will be there. Okay, so finally that is for one compound, but for finally for the entire reaction, how you will calculate is you will multiply that del del H factor into the number of oxygen molecules that are being consumed in the system. So you will first find out how much of energy is used if the compound is being oxidized, and totally how much of compound is being destroyed can also be notated by how much of oxygen was used. So you just multiply those two values and you will end up having your del heat of reaction. So all this is based on whatever is given in your problem and whatever condition is being stated in your problem. The problem is going to read that it is aerobic process and it gives you the chemical formula for the compound, and it tells you, it gives you an equation or it tells you how much of oxygen is being consumed. Then you can use the last formula. In all other cases, what you do is either you are directly given the del heat of reaction itself, or you will be given the specific enthalpy of your reactants and products as well as the mass of reactants and products that are entering and leaving the system respectively. So you have to multiply these values and then you have to find out the del heat of reaction. And but for the entire energy balance itself, only the del heat of reaction is not the whole point. It's about in what other ways heat is leaving the system or entering the system. That is your Q and Ws value as well as the latent heat of vaporization, which is the water evaporating factor. So these are the whole factors that you have to consider for energy balance. Is that fine? Okay. Okay, so with that, we'll start with this week session officially. Like that was just a doubt from previous class. So we are in the week 4 practice session for the fundamentals of bioprocess engineering course. And yeah, the week 4 contents include enzymatic immobilization, external mass transfer, internal mass transfer, and the applications of immobilization. So if you have any specific doubts from the last 4 weeks contents, any of the contents, you can just post it in the chat box anytime. I will just see them and respond to it. Apart from that, we'll just start solving some questions. We have mostly problems, but one or two concept based questions also we have for today. So I'll just display the first question. You can try to answer, and then we'll discuss each concept based on the question itself. So an enzyme is to be used continuously in a stirred reactor. The enzyme has the following characteristics. It is expensive, highly soluble in water, sensitive to chemical modification. It must retain almost its complete intrinsic activity. The reactor experiences relatively high hydrodynamic shear, and the recovery of enzyme from the reaction mixture is very essential. So, provided all these conditions has to be satisfied, which immobilization strategy do you think is the most appropriate? Name the strategy in the chat box, as well as maybe a single sentence of why you think that strategy would work for the given condition is also required. As always, I'll wait for a few minutes for you to think and answer for this question, and then we'll discuss. Okay, one person has told that membrane entrapment as it doesn't alter the enzymatic activity. Okay, any other methods anyone would choose, or the same method for some other reason? Okay, I guess there are no more answers. Entrapment is the most suitable technique for enzyme immobilization in this case because it provides physical confinement and it avoids the chemical modification of the enzyme, because that is the main point here. It's sensitive to chemical modification, and only if that doesn't happen, then comes the others like retaining the activity and all. And also it is a highly soluble in water, so the options that you might have in mind would narrow down at that point, and then when it's sensitive to chemical modification you end up choosing entrapment. So why not covalent bonding and cross linking? Because they are chemical modification techniques and they have high risk of affecting the enzyme's active site. And adsorption is again a physical confinement technique, but the key here is it has relatively high hydrodynamic shear and the adsorptive forces are not that strong. So, there can be desorption where the enzyme can come out of the matrix and it's no more immobilized. So that's the reason between adsorption and entrapment you would choose entrapment. So it's clear that you will not choose any chemical modification technique, but within the physical, you predominantly have adsorption and entrapment. And when you talk about this high hydrodynamic shear, then you end up choosing membrane entrapment. This is also one more a startup question, like another simple question like the previous one. The substrate is a small soluble molecule. Enzyme must not leach from the support, and the reactor operates under strong agitation. So here also you have high hydrodynamic shear, and the condition is that maximum enzyme retention is required. A moderate reduction in the activity is acceptable. So which immobilization method could we choose? Okay, covalent immobilization. Anyone else wants to answer? Wants to try? Okay, so two people have told it's covalent binding, and that's right. So because it provides a strong and stable bond between the matrix and the enzyme. So here also we have a high hydrodynamic shear, so it will not come out. And last question, we do not want the enzyme activity to be much deteriorated. So that's why we went for a physical adsorption. But here we are told that yeah, we can have a moderate reduction in enzyme activity. So it's better that we go with some chemical modification, trading off with the activity itself. So covalent binding is suitable here. So like this, just have in mind when to go for which type of treatment, immobilization technique. Another question, we'll just quickly see this question. I'll just wait for a couple of minutes only. So first statement says that immobilization can increase enzyme stability. Second is immobilization always increases the intrinsic catalytic activity of the enzyme. I think this is a pretty easy question. You can just answer and then we'll go solve some problems. Exactly. So immobilization can increase enzyme stability, whereas it does not always increase the catalytic. Like we just saw that the catalytic activity may be reduced because of chemical modification. Okay, we'll start with some easy problems and then just go on solving problems of different concepts that we saw in immobilization. The first one is an initial enzyme solution contains 1200 units of enzyme activity. After immobilization, the immobilized preparation shows 840 units of activity. The recovered liquid contains 180 units of activity. Calculate the coupling yield. The very first formula you might have seen in this topic. Okay, I see someone raising hands. If you have any doubts, you can just post in the chat box or unmute and ask. So the coupling yield is like calculated from how much of the enzyme is removed from the initial solution, right? So the difference between you can you calculate also the bound activity or sorry, can you also calculate the activity yield? Okay, so in by coupling yield, what we mean is like how much of immobilization has taken place in the system. That is, the amount of or the percentage of enzymes that has been um, like successfully being transferred to the support matrix. Okay, so that is what is coupling yield. When we talk about activity yield, before immobilization, what was the activity of the enzyme, and after immobilization, how much is the activity? So, based on that, you will calculate your activity yield. Um, After immobilization, the activity might decrease. We saw that because of some chemical modifications and stuff, they can be decrease in the activity. So, to talk about your answers. Here, whatever is asked is whatever was initial present, how much is recovered, and how much was the initial. All these three terms only you will need to find the coupling yield. It tells about the physical bonding that has happened between the matrix and the enzyme. I guess for this 8, whoever got this 82.35, you have maybe found out the immobilization efficiency. Like, I mean, maybe you got it by also having subtracted denominator. So I think that's an immobilization efficiency. And maybe you can recheck that. But coupling yield, what I mean here is how much of that bonding has happened between the enzyme and the matrix. Okay, so the next question is that an enzyme is immobilized on an anionic carrier. The substrate is positively charged. Uh, which of the following is most likely? Okay, exactly. So B is the correct answer. The local substrate concentration near the enzyme increases and the apparent Km decreases because an anionic carrier is going to attract the positively charged substrate. Therefore, the local concentration near the immobilized enzyme will increase because of the electrostatic attraction. So, sorry. And when this was discussed, you can also see that the opposite charges can result in decrease in apparent gain. Okay. So the next problem is a soluble enzyme has Km equal to zero 0.5 millimolar and Vmax is 120 micromole per minute. After immobilization on an oppositely charged carrier, an apparent Km decreases by a factor of 10 due to electrostatic attraction and apparent Vmax decreases by 40% due to diffusion limitation. For a substrate concentration of 2 millimole, you have to calculate the following and then explain why immobilized enzyme can have lower Vmax but a higher rate at low substrate concentration. I think the first four questions are very easy and this question is also kind of so familiar to you. You might have seen this in your lecture note itself. Okay, so the Km apparent, because it decreases by a factor of 10, it's 0.05 millimole, and your Vmax apparent is, your Vmax apparent has a 40% decrease, which means it's 60% of the original. 60% of 120 is 72 micromole per minute. And the next question is the immobilized enzyme rate. So it's Vmax apparent into S by Kmax apparent plus S. You have to use the values that you found in the previous two questions, and the rate is 70.24 micromoles per minute. And then for the soluble enzyme, you just have the Vmax as 120, and you know your Vmax S by Km plus S similarly. So it is 96 micromole. Up to this, I think it was doable because that was very basic, and you have to explain like why Vmax is decreasing. So that was the final question. So your immobilization has two competing effects. One is electrostatic attraction, where your Km will decrease and it improves the substrate affinity. And one more thing is the diffusional limitation. So your diffusional limitation is also being altered, so your Vmax lowers. So it reduces the maximum observable rate. So at very low substrate concentration, what happens is the reduction in Km uh, will try to compensate for the reduction in Vmax. So you can see all these factors: reduction in Kmax, Vmax, in enzyme immobilization bioprocessing without contradiction. So both these opposing factors act together in an immobilized enzyme system. So that is why you tend to see them. Okay. So an immobilized enzyme follows Michaelis-Menten kinetics, and you can note down what is the Vmax, Km, the bulk substrate concentration, mass transfer coefficient, times surface area per uh, unit reactor volume. All these values you can note down now. Your Vmax apparent, all these values you can first note down. So based on this, you should tell about external mass transfer, external mass transfer, approximate surface concentration, and the reaction rate. the observed reaction rate. So talking about enzyme immobilization, you just have concepts and you derive the enzyme kinetics accordingly, and you just have equations and formulas to solve. So that is what we'll be doing today. So if you have any doubts in between, you can just let me know. I have just tried to add problems similar to your lectures so that it just be like a practice for you. Wherever possible, I have tried to add some conceptual analytical questions. So, but mostly it is going to be usage of formulas. From the given data, you have to find the external mass transfer, surface concentration, and the reaction rate. Okay, so here you are given with a maximum reaction rate of 1 into 10 to the power minus 3 moles per meter cube per second. The maximum mass transfer rate based on the bulk concentration is RMT max. So that you can find using KLA into CB. So you have both the values, and that gives you 5 into 10 to the power minus 4 moles per meter cube per second. But Vmax by the RMT. Vmax by the RMT determines your external mass transfer. So that is 2, which means your Dam-Kohler number is having a value of 2. Here it is greater than 1. So external mass transfer resistance is significant in this case. So when people talk about external mass transfer, whether it is important, significant, all means the same. For that you will require your Dam-Kohler number. Based on the value of the Dam-Kohler number, you will say if the external mass transfer is significant or not. So if it is less than 1, then it's other case, but here you have a Dam-Kohler number of 2, which means your external mass transfer is significant. And for surface concentration, uh, the first form is what you will be needing. You have to solve that equation, right? So you have the equation and you have to solve for this equation. So in order to solve for this equation, you are going to divide both sides by 5 into 10 to the power minus 4, or it's the same, divided by 10 to the power minus 3 multiply 0.5, it's all the same. any strategy. And then the common factor that you have is zero point 0.2 plus CS. So when you multiply that as well and solve, this is just basic equation solving. You just take common terms, multiply, divide, all that, and finally you end up having you will have a quadratic formula where c square plus 1.2 cs minus zero point 0.2 is equal to 0. So with however you solve it, you will finally end up with this is the starting equation. So you have this equation and now you are bound to solve for the CS value. The question that was asked is your surface concentration. So you are going to solve based on the equation that is given here. Okay. You have taken the value and when you solve, you will get your CS value as 0.16 or 0.15 mole per meter cube. Like when you solve using different ways, you will end up with that. But anyways, it's approximately 0.16 moles per meter cube. But what is your CB? The bulk concentration is 1. So, but your surface concentration is way less, and this also tells that there is significant external mass transfer. This is your surface concentration. I hope you get how to solve for this. KLA into CB minus CS is equal to Vmax ACS by Km plus CS. You take that equation and solve it to find CS. Substitute all other values and solve. So when you compare, you find that there is external. The first question was about external mass transfer, right? So you can just compare and check here. And the last one is the about the observed reaction rate. So the reaction rate is 10 to the power minus 3 into 0.16 by 0.16 plus 0.2. I hope you get where the equation comes from. So all equations are given here only. This was the first step. And your reaction rate is going to be 4.4 into 10 to the power minus 4 moles per meter cube per second. And I mean, if you see your KLA value and this are somewhat near. So whatever you find out, just compare it with the values and understand how the process can work. I hope that question was also not very difficult, but I didn't see any of your answer. If there is any difficulty regarding that question, you can just ask me. And this is the last question for today, though we have enough time. You can take your time to solve this. Like an industrial biocatalytic process uses immobilized enzyme beads to convert a soluble substrate. Okay, you have to assume Michaelis Menten kinetics. These are all the given data in the problem. Now you have to calculate all the, you have to answer all the 7 questions given here based on the given data. We can just solve one by one. So after every few minutes, I will just tell the answer for one of the subdivisions. So you can just start solving the question. This is kind of an overall question where we deal about many concepts in enzyme immobilization. So the formula to find Damkohler number is dA equals B max by KSA into CB, and all the values are given in the previous slide. I hope you noted down all the values. So yes. Here Vmax is 0.04 gram per meter cube per second, Ks is 1.5 into the power minus 5 meter per second, A is 150 per meter, and Cb is 5 gram per meter cube. When you substitute all the values here, you will get a Damkohler number value of 3.56. And also here in this particular scenario also, your external mass transfer is very significant because your Damkohler number is greater than 1. The second question is to estimate the substrate concentration at the particle surface by solving for the given equation. So this just right before this question only we saw how to solve for it. Similar strategy you have to use and solve for CS. So for your second question, you have Ks and A, multiply those Ks into A and you will end up with 2.25 into 10 to the power minus 3 per second into Cb, you know, which is 5 gram per meter cube. Cs is what you have to find out. B max is 0.04 gram per meter cube per second into Cs divided by Km is 20 gram per meter cube. So you have an equation now. You just bring it in the form of a quadratic equation. So in the way I solved, what I did was I just had this, all the values substituted, and there is this equation. To this, multiply both sides on 20 plus Cs. And then expand each term, add similar terms like you have. And finally, the equation that I got was 2.25 Cs square less 73.75 Cs minus 225 equals 0. This was my final quadratic equation. I just substituted all the values given here into this. The only remaining factor is Cs, and I just expanded the entire equation such that I end up with a quadratic equation with Cs. And finally, this is the quadratic equation. And when you solve for this quadratic equation, as rightly mentioned, you end up with your Cs value as 2.81. Cs is 2.81 gram per meter cube. The first one was also easy because you know how to find a dA, just substitute. Second one, equation is also given, everything is given, you just have to solve. And the third one is your external effectiveness factor. I hope you are able to solve until now. If there is any difficulties, please let me know. I'm assuming that you are able to solve. So next question is about your external effectiveness factor. So how you can find your external effectiveness factor is the it can be the ratio of your observed rate and the ideal rate that has to be in the equation, right? I mean in the system. Ideal rate is whenever there is no external resistance, what would be the rate? But with the resistance, how much of the rate is observed? So when you have these two values, then you can find out the external effectiveness factor, which is the eta external. So in order to find the observed rate, you go with KSA into CB minus CS. You have all these values again, so you just substitute and find your observed rate, and your rate without external resistance, it is going to be ideal or the maximum rate. It is Vmax Cb by Km plus C. This is under ideal conditions where we assume there is no resistance, maximum or ideal. So the ratio of the observed rate and your ideal rate is your external effectiveness factor, and to find the observed rate you use the formula KSA into CB minus CS, and to find the ideal rate you use the formula Vm into CB by Km plus CB. All the factors, all the components of this particular equation is already given. So if you just substitute the given values, your R, the observed rate is going to be 4.93 into 10 to the power minus 3. Unit is gram per meter cube per second. Similarly, when you're going to substitute all the Vm, Cb and Km values here, your ideal rate is going to be 8 into 10 to the power minus 3. Again, grams per meter cube per second. So be careful with the units. Sometimes don't miss the units here. Obviously, you're going to find the ratio, but the unit should be same before you find the ratio. And with this, you end up getting your external effectiveness factor as 0.616. Right. So external effectiveness factor is a ratio of the observed rate and the ideal rate. You have to know the formula to find out the observed and the ideal rate. Then you can easily substitute and get the value. This was the third part of the problem. So instead of giving different problems, it's just one and making you solve for different factors. You have to calculate the internal Biot number. The next is the internal biot number. So to find your, okay, so to find your biot number, BI is equal to KSR by DES. You have the values. Let's just go back and check the values once. R is 2.5 into 10 to the power minus 3 meter, and DES is 2 into 10 to the power minus 9 meter square per second. So, and Ks is 1.5 into 10 to the power minus 5. So, if you directly substitute all the values, your internal biot number is going to be 18.75 as mentioned here. And in case of your biot number like Dam-Kohler number, you have the effects of the value of the number. So if the BI is less than 100, then external mass transfer still influences the overall rate of your reaction. This is how you find your internal biot number. Formula is BI is equal to Ks into R divided by DES. Next question is your TEL modulus and internal effectiveness factor. At least up to TEL modulus, I think it will be easy for you to solve. What's the value of TEL modulus? I mean, the entire equation is given here. R by 3 into square root of V max by Km into ds. This V max by Km is your K effective. So, and all the values are given here. Any answers for TL modulus? Okay, if you directly substitute the values for TL modulus in the from the given and into the given equation, the TL modulus is going to be 0.833. It's going to be 0.833. So the equation was also given and the values were also given. And what happens next is your internal effectiveness factor. That is kind of a difficult question for you to answer now. But when you talk about first order sphere and the internal effectiveness factor, eta I, the equation comes out to be so this is a formula to find your internal effectiveness factor. And if you solve for this using your TL modulus, you will get an internal effectiveness factor of 0.402. And the last two questions are about overall effectiveness factor and suggesting practical modifications to improve the process performance. So the formula for your overall effectiveness factor is going to be, this is eta overall. Okay. Your internal effectiveness factor into your Biot number divided by 1 plus Biot number is what you call as your overall effectiveness factor. So if you just substitute this and this, finally you will end up getting 0.382. So overall, only 38% of the kinetic rate is observed. Like it can, let's say it can perform 100%, but the what you observe is only 38% because of both external and internal mass transfer limitations. So this is simultaneous external and internal mass transfer in your enzyme immobilized system. And your final question comes out to be suggesting practical modifications to improve the system. So one is to reduce the bead radius. So when you reduce the bead radius, TL modulus will decrease, diffusion path length will also decrease. If your TL modulus and the diffusion path length are going to decrease, then obviously your this factor is going to decrease. Sorry, this factor is going to increase. So how you can see? You can see that your TL modulus is what determines your theta I, right? So in that case, if you are going to decrease your TL modulus, then your efficiency is going to increase. How to decrease your TL modulus? One basic step is to reduce the bead radius, and next one is increasing the flow rate. How do you increase the flow rate? By increasing the agitation. So this will eventually increase your Ks value. This will eventually increase your Ks value. From this equation, if you increase your Ks value, you see that your Biot number is also increasing, which means your external mass transfer resistance is going to decrease. So first one is to reduce the bead radius. If you reduce your bead radius, see, you can also trace it back. You want higher eta I value, which means you have to reduce your TL modulus. One way of reducing a TL modulus is your reducing your bead radius. Next factor is your Biot number. If your Biot number is increasing, then the external mass transfer is decreasing and you can improve the process. So how do you do that? When you are going to increase the agitation outside, then your flow rate will increase and your Ks will increase. All this is connected. That is one. Apart from that, you can operate this at a higher bulk substrate concentration to reduce the diffusion gradient effects. So that is like an operational thing. You may be able to carry it out using the given system or not, but that's also an option. And finally, you can optimize your enzyme loading to balance the activity and diffusion limitations. I hope that was clear. Do you have any doubts? You want me to repeat anything? This is what I told now. Any doubts? That was all for today. So I had some theory concepts and problems based on the enzyme immobilization. So if there are any doubts, post in the chat box. Otherwise, thank you all for joining in for the session. I hope it was useful. If there are any other suggestions, comments, or doubts, please post in the chat box. I'll just wait for a few more minutes. We have some more time, so I can just wait. If not, again, thank you again for joining in. Hope to see you in the next session. Next session is about your growth kinetics. So yeah. Any doubts? Okay. Thank you for joining. Thank you so much. Okay, if there are no doubts, I am just closing the session. Thank you for joining and welcome to the next session, the next week. See you next week.